Hello everybody. If you're coming here from Steve Mould's channel, you probably have some idea what you're looking at. Otherwise, you're probably very confused. Here goes something. Ta-da! Let me explain. There's a thing called the Spool Paradox, or at least that's what Steve's calling it, and that's what I'm going to call it too, because it's good enough, and we're not going to get pedantic about what's a paradox and what's not a paradox. That's what the comment section is for. Anyway, Steve's video does a much better job of explaining it than I care to, and there would be no point in trying to reinvent that. So go check out his channel to watch his video about it, to learn the sciencey part. I will just plagiarize a little bit here, but go watch his if you really want to understand how this works. Essentially, if the radius of the rope is larger than the radius of the spool, it'll go one direction, and if the radius of the rope is smaller than the radius of the spool, it'll go a different direction. But I was immediately curious, what happens when you approach the point where the radiuses are the same? And I saw in the comments that a bunch of people were also really interested in knowing what would happen. So I built it because I had to know the answer, and maybe someone else will think this is interesting too. I'll give you a little tour of this setup so you can understand how this works. Critical, of course, is the spool. It's just a empty roll of 3D printer filament. As Steve mentioned in his video, friction is a big factor in whether or not this works, because if you pull on the spool really hard, it's just going to slide along. So to remove friction as a factor in this, I attach gears to it, and the whole thing has to roll along these rails, and it can't just slide. I mean, if you pull hard enough, it'll just cause the whole thing to explode and fall apart. That happened once. It has a lot more glue and tape now. I didn't have any thick rope around, but what I did have was this thick silicone tubing. And really the only thing that matters is that you can roll it up and it's thick. I'll explain why the thickness matters in a minute. To add a pulling force on the spool, the rope, I'm just going to call this rope from now on. The rope goes all the way down the end here, over the top, a little roller, and there's just a bucket hanging from the end. So I suppose you could say this is gravity powered. I used a bucket in case I needed to add more weight, but just the weight of the tubing and the bucket and the clamps was enough to make this work. I mentioned that the thickness of the tubing was important, and here's why. In order for this little setup to work, we need the radius of the rope to change quickly. Theoretically, it would work if the radius changed really slowly, but if it changes slowly, it's going to have to roll a lot farther before it reaches the point where the radius transitions. The other thing is, if it doesn't transition quickly enough, there's going to be a really large dead zone in the middle, where essentially the mechanical advantage of pulling on it is going to be too much or not enough, depending on how you're thinking about it. Basically, when it's at its equilibrium point and you pull on it, nothing's going to happen. So if the range is too big near its equilibrium point, there's going to be a huge range where pulling on it doesn't do anything, because this isn't a completely perfect system with zero friction in any way. Theoretically, if this was a spherical cow in a vacuum, it would totally work if there was no friction anywhere that we had to worry about. But since we're here on Earth, we got to overcome that. So then, in order to overcome the problem of getting the radius of the rope to change quickly, step one, use a thick rope. So the thickness changes really quickly as you wind it up. And the other thing that I had to do was make sure that it piles up as quickly as possible. So I just taped some cardboard in there to make sure that it's only spooling around in the thickness of the rope itself. So it can't go next to it and, roll around a whole bunch of times without actually increasing the radius, because it's just lining up next to itself. Every time it rolls around, it has to gain at least one rope thickness worth of radius. And that's the key to making this actually work. So with all of those considerations taken care of, it actually works. I was very pleasantly surprised that it actually worked, because I was really not sure if it was going to work or not. Every time you push it in one direction, it'll roll right back to its equilibrium point, where the radius of the spool is the same as the radius of the rope. It doesn't matter which way you go. It's just the bucket pulling on the rope will always put it right back in the center, which is kind of awesome. In case you were curious, here's how the bucket moves when it rolls back and forth. Make a prediction about how much you think the bucket's going to go up and down. I was a little bit surprised by what it actually does. My prediction about the bucket was completely wrong. I was thinking that the bucket was going to go up a lot, no matter which way I rolled the spool up. But that was not the case. I think the reason why it doesn't work that way has to do with two different things. One is how far the spool is away from the bucket, because the whole spool itself is moving. So when the spool is moving away from the bucket, if it wasn't rolling at all, that would be raising the bucket. When the spool is moving towards the bucket, that would be lowering the bucket. So I think that's variable number one. And the second one is how much rope is wrapped around the spool and the radius of the rope, because that determines how quickly the rope is going onto or off of the spool. So when you're going away from the bucket, the radius is getting smaller, and it's letting out a lot less rope every revolution. So that's going to pull on the bucket a lot more. It's going to cause it to travel farther. However, when it's getting closer to the bucket, it's wrapping around, making the radius of the rope larger on the spool. Then it's pulling in a lot more rope with every revolution. So it's counteracting the fact that the spool is getting closer to the bucket. That's my armchair physicist explanation. I'm not going to do any math. Let me know in the comments if you think that's the right explanation or if I completely missed something. I feel like there's a lot to unpack here, which is why it's kind of interesting in the first place. This is definitely one of the most useless things I've ever made, but boy is it satisfying to watch it roll back to the middle every time. So let's enjoy some more rolling around B-roll. If anyone tells you that you can't do real physics research with scrap lumber, cramps. If anyone ever tells you that you can't do real physics research with scrap lumber, clamps, tape, and hot glue, well, they might be right, but you can definitely still learn something. And that's good enough for me.